I have been given a topic to talk about is high-speed rolling stock. So I start my talk. The contents of my presentation will be, to start with, I will be giving a overview of Mumbai-Ahmedabad high-speed rail project, a brief status, and if time permits, I can show you a progress video. Coming to high-speed rolling stocks, I will be talking in general first about the type of rolling stocks world over and rolling stocks in Europe and Japan particularly. Why I am talking about Europe and Japan? Because China or Korea, they are derivatives of the rolling stock from Europe and Japan. Then coming back to the Mumbai-Ahmedabad high-speed rolling stock, I will be talking about the key parameters, silent features. Since I have been given only 15 minutes or 20 minutes of time, maybe if time permits, I would like to talk about energy efficiency of the high-speed rolling stocks, air tightness, noise, and aerodynamics requirement. It depends on the time and the response from the audience. So, to begin with, as many of you must be knowing about the Mumbai-Ahmedabad high-speed rail project, it starts from Mumbai to Sabarmati in Gujarat. It is a 508 kilometer long project. Around 348 kilometer lies in Gujarat. Around 155 kilometer lies in state of Maharashtra. The entire alignment is on the viaducts, bridges, and tunnels. There will be around 12 stations en route. The train will be running at 320 kmph, and the travel time will be around 2 hours 7 minutes for the limited stop train, and around 3 hours for the all stop trains. The status of the project is that all the contracts of Gujarat portion have been awarded, all civil contracts, bridge contracts, and track works. And the work is going on the viaduct on the entire section of Gujarat, all 8 stations, rivers, and all bridges. For the Maharashtra portion, we are going to start the work very soon as the land acquisition has started recently. Coming to the high-speed rolling stock in general, I'm not sure about the audience. I may be sounding a bit technical. I would try not to be technical, but since the topic is high-speed rolling stock, we must know what is the high-speed rolling stock is and how it is different from the conventional rolling stock, particularly metro. A lot of talk was on metro from the previous speakers. What is a metro? What is the semi-high-speed train or RRTS train? And what is high-speed train? So, if we see the types of rolling stock, high-speed rolling stock, which are working in the world, traction power-wise, there are 2 types of rolling stock. One is distributed traction, and one is the concentrated traction. The distributed traction is basically prevalent in the country of Japan, China, Germany, and Italy. Whereas concentrated power is in France, Korea, and Spain. When we say concentrated power, that means there are 2 locomotives at the top and at the tail of the train. Whereas in distributed traction, the propulsion is distributed all along that train. Then if we take the mechanical part of the train, there are non-articulated trains where we have 2 bogies on a car, and you have an articulated train where the bogies are shared by 2 cars. Both the configurations are prevalent in the world. The not articulated, that is normal trains, are Shinkansen trains with distributed power traction. The IC trains of Siemens in Germany, they are again normal trains and distributed traction. And by Alstom, it is Pendelino train, which is also a distributed traction. In articulated, you have TGVs and AGVs from the Alstom, both in concentrated power and in distributed power. There is a special type of train at the bottom which is called articulated single axle train, where there is a single axle. In fact, it is not an axle, it is a pair of wheel between two cars, and that is called the talgo trains. It is tilting trains, passive tilting trains. We'll be talking in brief about these technologies. So as you can see that distributed traction, where the traction motors and propulsions are distributed all along the train, whereas in the concentrated, there are two locomotives at the front and the rear of the train. The advantage of distributed traction is that you have more seating capacity. Around 20% more seating capacity is there in the distributed traction system. The advantages of distributed traction system is low axle load. The advantage of concentrated power is low noise and low maintenance. Moreover, since the propulsion is concentrated in the front and rear of the train, there is no passenger, so in case of any traction fire, the passengers are not affected. But recently the trend is towards the distributed traction, because you can mitigate all those issues of concentrated traction with the advent of new technology of better noise insulation and better fire performances. The key point of the distributed power train, that is EMU train, is the low axle load, for which the recent trend is for these type of trains. Then when it comes to the bogie parameter, it is articulated train, where as you can see in the top, the bogies are shared by two cars. Here the number of bogies are less as compared to the normal train. However, the number of cars increases. The advantage of articulated trains are they are more comfortable, less noisy, less energy consuming, and they are more stable and safe. The disadvantage of articulated trains are that the length of the car reduces, so you have a lesser passenger capacity. The higher axle load because of less number of bogies, and uncoupling of cars becomes difficult in case of articulated trains. But both type of configuration is all prevalent in the world. Then we have a single deck car or double deck car, depending upon your carrying capacity. If you don't want to increase the length of that train and you want to carry more passengers, you go for a double deck structure. So a double deck car or double deck train offers around 15 to 25% increase in the passenger capacity for distributed traction, and around 35 to 40% increase in passenger capacity for the concentrated power. It is because in the concentrated power you can lower the floor because you don't have underslung equipments. Then there is a type of train called tilting trains, where on the existing curves, if you are not able to eliminate the curves on your alignment, you go for tilting trains where you can increase the speed by tilting the train. There are various technologies available for tilting the train. On the left side of the screen, this is called the first left three figures are active tilting, and the right two figures for the passive tilting. Active tilting is basically you initiate the tilting by an action. For example, on the leftmost picture, you can see the tilting is done by increasing the height of the air spring. In the hydraulic tilting, it is by the hydraulic actuator you tilt the train. Whereas in case of passive tilting, it is automatic tilting of the train because of the curve, because the center of gravity of tilting is above the center of gravity of the train. And on the rightmost picture, you see the natural tilting train by Talgo, where you can see there is a set of a pair of wheels on which a special arrangement is made, and the car body is hung from the top. So when the train goes on the curve, it automatically tilts naturally. The advantage of tilting is that you can have higher speeds so that you can save 10 to 15% of the time on the sharper curves, and overall time reduction is around 10 to 15%. The disadvantage of tilting is motion sickness, and in case of there is extra wear on the tracks and on the wheels also, and there is a risk of overturning if the wind speed is more. So normally the alignment of high speed is designed in such a way that you don't have sharp curves, but in case you are not able to avoid the curves, you go for tilting trains. Now I talk about some of the trains which are prevalent in Europe and Japan. I start from the very beginning of Europe is 1993. It started, it's called TGV train, which operates at 320 kmph. It is a concentrated power train with articulated bogies. Then you have TGV duplex, is a double deck train introduced in 1996. It is also a concentrated power train capable of running at 320 kmph with articulated bogies. Then there is a Talgo passive tilting, natural tilting train introduced in 2005. It is a concentrated train with a speed potential of 300 kmph. Then AGV by Alstom introduced in 2012. It is a distributed power. In France, normally you get to see the concentrated power train, that is loco haul trains. AGV is one of the exception where it is a distributed power train capable of running at 300 kmph on articulated bogies. Then in Germany, you have ICE trains, Velaro series of trains with distributed power with a speed of 320 kmph, introduced in 2013. Then there is a ETR 1000 train by Bombardier. Now it's taken over by Alstom now. This was introduced in 2015 with a distributed power with a speed capability of 300 kmph. This train is a Pendolino train which has a tilting arrangement. The speed is 250 kmph and 8 degree of tilting is possible in this train. It is manufactured by Alstom. The next train is Avril by Talgo, which is a passive tilting train. It has not come into the service, but it is under testing, and it is with the passive tilting arrangement. The Velaro Novo is a new train planned in 2023 of Siemens, having a capacity of speed capability of 360 kmph on distributed traction. These are the new trains. Then TGV Avelia Horizon is planned in 2024, capable of 360 kmph, and it is a loco haul train with articulated bogies. When you come to Shinkansen trains in Japan, there are two types of train I will be talking about. One is this N700 series train introduced in 2013 with 300 kmph operational speed with a 1 degree of tilting. This is the train E5 which is being talked in India very much, because based on this train, the train of Mumbai-Ahmedabad project will come. It was introduced in 2011 with a distributed power, with a speed capability of 320 kmph and a tilting capacity of 2 degrees. So having discussed all the major rolling stocks which are running in world, I come to the main high-speed rolling stock of Mumbai-Ahmedabad. As I told, it is based on E5 series train of Japan. So it will have 3 types of class. One is standard class, business class, and first class. The seating capacity will be around 730 seats in a train. It will be a 10-car train. The speed potential will be 320 kmph. And on the start of the revenue operation, we require 24 number of trains. And after 10 years, we have to augment the number of trains. We will have 11 more trains of 16 cars. And after 20 years of service, we will have 44 trains requirement of 16 car. And after 30 years of service, we will have 71 trains of 16 cars. This depends upon the ridership and traffic density. This is the configuration of 10-car train, where car number 1 to 8 will be standard car, standard class. The car number 9 will be business class, and car number 10 will be the first class. This will be the seating arrangement. For the standard class, it will be 3x2 seating. In the business class, it will be 2x2 seating. In the first class, it will be 2x1 seating. There will be one car of business class and there will be one car of first class. The key parameters are that the trains are wider in Japan. The width of the train will be 3.35 meter, whereas in Europe, normally it is 2.9 meter. The axle load will be around 14.8 ton, maximum axle load, which is also a very significant departure from European trains, where normally the axle load is 17 ton. These are the salient features of the train, which we are going to have in nutshell. It will have aerodynamic car body design. The cars will be airtight and pressurized. There will be noise control measures all along the train. There will be active suspension to have a comfortable ride. There will be automatic seat rotation. So this is the salient features of a high-speed train which we are going to have. I can discuss in detail if the time permits, and I'm panelist. I mean the regulator can another 2-3 minutes. Okay. So what I do, I skip all the slides now and straight away go to just a interesting topic about of the aerodynamic requirement. I think this, it is different from the conventional trains. You require aerodynamic shape of a train when the train goes beyond 300 kmph or maybe 250 kmph. And because you have to, the air drag produces a lot of resistance, so the nose has to be quite long and very specifically designed to reduce the air drag. And the second problem is when the train enters in the tunnel, it produces a lot of turbulence inside the tunnel. And when the train exits the tunnel, it releases a lot of micro pressures, and an explosion sound is heard. So to avoid this, you have to have a very special kind of nose, a long nose of the train. And for the E5 train which we are having, the train has been designed a 15-meter nose, and the inspiration came from duckbill, the beak of the duckbill, and scientists studied that with this shape of the front of the train, you can easily go inside a tunnel at a speed of 360 kmph. I think this is all I have time. I would like to just show a small video of the progress that we are doing in the state of Gujarat. Sound. So here the alignment I'm showing is for the Gujarat portion from Valsad to Ahmedabad. All the civil works are going on. This video is of around 4 minutes. It will show you the progress overview. The green dot shows that where the video is from. Right now it is showing the Valsad region of the Gujarat. Yeah. Thank you. This video is also available on the YouTube, on our website also. Thank you.